Hello, welcome back. We will continue our discussion of the linear instability analysis of a two fluid interface. Let us quickly recap what we have done thus far. We are looking at the stability of an interface formed between two fluids. Say I have a fluid of density rho 1 superimposed over another fluid of density rho 2. The fluid of density rho 1 is moving with a velocity u 1, the fluid of density rho 2 is moving with a velocity u 2. Rho 1, rho 2, u 1, u 2 are all constants. We started with our basic governing equations and boundary conditions, and we quickly substituted this base flow given by rho 1, rho 2, u 1, u 2 into the governing equations plus the boundary conditions to check that it satisfies the equations, as it does. Then we introduce a small perturbation to this base flow field, which we denoted by the primed quantities u I prime, v I prime, p I prime, etc. And we substituted the perturbed flow fields into the governing equation and boundary conditions and linearize the flow. So, the first step was to linearize the flow field about this perturbation, about this base flow field. Okay, so, that gives us a set of linear partial differential equations that will describe the growth or decay of the perturbed quantity. The next step that we followed was to assume a particular form for the perturbed quantity called the normal mode form. We wrote these in equations 14 to 16. And we are now at a point where we know we have our linearized governing equations in equations 8 to 10 and the normal mode form in equations 14 to 16. So, we begin by our solution process allowing us to substitute when we perform this substitution. What we get we get these three equations, the first one coming from the continuity equation, the second one from the x momentum equation, and the third one from the y momentum equation, just for our reference. The double prime quantities are only functions of y, just so we recall, and that is the reason the derivatives of the double prime quantities with respect to y remain, but with respect to either x or time are simply converted into an algebraic multiplication with either ik or omega, or as the case with the advection term omega plus ikui. So, from these equations we are now able to, we want to get a single ordinary differential equation if we can for pi double prime by eliminating ui double prime and vi double prime. So, let us see what that process looks like. So, we are able to write down ui and vi. Ui double prime is minus ik over rho I times pi double prime divided by omega plus ik ui, and vi double prime from 18 or from 19 is given by this. Now, I can use these two equations and substitute into 17. So, in order to do that, I need to take the derivative of the equation for vi double prime with respect to y, and that is what I have done here. Now, when I substitute the equation, substitute this equation and this equation into (17) here, which is what we got from continuity. Okay. So, for in short, I can write this as this is our equation 20. Now, remember I equals 1 or 2, we have maintained that notation all the way through from the beginning of this derivation. So, essentially P1 and P2 are the static pressures in fluids 1 and fluid 2, and they are independent, they are separate. So, I am going to solve for them separately, and from there I will find okay. So, that is our location of the two fluids 1 and 2. 1 is located in the region y greater than 0 and 2 is located in the region y less than 0. So, this is the most general form of the solution of equation 20. Now, if you think of fluid 1 for a moment, for all y greater than 0, and remember k is a positive number in our temporal linear instability analysis, k is a positive real number. So, if k is a positive real number, then this first term here C11 e power ky is going to become increasingly larger as y increases. But the static pressure in fluid 1, especially noting that these are all little p, these are all lowercase p, meaning they are perturbation quantities. The perturbation quantities have to remain bounded. So, for the perturbation quantities to remain bounded and this to be the solution, the only possibility is that C11 has to be 0. C21 not being 0 is okay, because the e power minus ky function decays away exponentially for all y greater than 0. Okay. So, C21 does not have any constraint on it, but C11 has to become 0. Similarly, using similar arguments for P2 double prime y and noting that fluid 2 is located in the region y less than 0. So, if y is less than 0, k still being a positive number, e power ky is going to decay exponentially as y becomes an increasingly negative number, that is y goes from minus 2 to minus 3 to minus 100 etc. As y becomes an increasingly negative number, e power minus ky is already bounded, but that is not the case with e power ky is bounded, but that is not the case with e power minus ky. E power minus ky now becomes unbounded. So, therefore, in order for the whole static pressure to remain bounded, C22 must be equal to 0. So, now we are in a position to write down the general form of the static pressure in fluid 1 and 2, which is our single primed quantity. From here, now we already have a relationship between ui and pi prime, ui double prime equal to minus ik over rho I times pi double prime divided by the omega plus ik ui. So, using that we will be able to write down what ui double prime and is supposed to be. And similarly, I can write u2 double prime. I am not going to write it down, but you can see that once I know u1, u2, and I can also use the other equation I can use this equation to get to what V I prime would have to be. So, now that we have u 1 and V 1, let us also write down and V 1 double prime would be analogous, V 1 prime would be analogous. So, now we have the flow fields and we have two undetermined constants C 1 2 and C 2 1. So, let us quickly take stock of that. And we will use the two boundary conditions that we have, the kinematic and the dynamic, two sets of boundary conditions, the kinematic and the dynamic boundary conditions, to calculate the value for C 1 2 and C 2 1 such that we have a non-trivial solution for the problem. That is our goal. We do not want C 1 2 and C 2 1 to become 0, because if they become 0, then we are left with the trivial case that the base flow alone persists. We want to introduce a perturbation and study whether the perturbation will grow or decay. For that purpose, we do need C 1 2 and C 2 1 to remain non-zero. Okay. So, let us now write down our kinematic boundary condition. Just to recall, a kinematic boundary condition is basically a requirement that if I have a fluid particle on the interface. So, if I have a fluid particle sitting on this interface, that fluid particle remains on that interface at all points in time. So, if I have a meniscus kind of like that, and if this fluid particle is sitting here, whether the fluid particle is translating in whether the movement of the fluid is to the left or right or up or down, the fluid particle is not detached from the interface. That is pretty much the physical meaning of what we call our kinematic boundary condition. So, let us write that down. What that says is V 1 prime evaluated at y equal to 0 Okay. We have the same normal mode perturbation introduced to eta. Eta happens to be the actual physical perturbation that you have introduced to the wave. So, if you have eta to be of having some amplitude eta naught and some temporal frequency omega, like we have said before, and a wave number k, then the requirement that the y direction velocity in fluid 1 V 1 prime as we approach y equal to 0 from fluid 1, which is basically denoted by this quantity V 1 prime at y equal to 0 is equal to the physical movement of the interface or physical movement of the interface in an advected sense. So, dou eta dou t plus u1 dou eta dou x is basically an advection of that interface with a velocity u1. u1 happens to be the fluid velocity, the base flow velocity in fluid 1. So, once we figure this out, now substituting what we have for V1 into this, we get k times C21 So, simplifying, we see k times C21 equal to rho 1 times omega plus I k u1 squared times eta naught. Similarly, we have another kinematic boundary condition requirement for fluid 2, and from there we have essentially the same requirement, but written now from the sense of fluid 2. Now, substituting what we have for V2 prime in here, we get minus k C12 again simplifying, k times C12 equal to minus rho 2 So, we have C1 C2 and we have eta naught, which is the amplitude, the initial amplitude of the perturbation that was introduced. For non-zero eta naught, we want non-zero C1 and C2, that is our goal, like we said before. Okay, so, that we have one last boundary condition. This is basically a force balance at the interface. We call this our dynamic boundary condition. Let us rewrite it quickly. It says P1 prime minus P2 prime equals minus sigma So, if I have P1 prime and P2 prime in terms of C1 C2, and if I make that substitution, what do I get? C21 minus C12 simplifying, So, we have equations, just as a quick recap, 21, 22 and 23 are homogeneous equations and we are looking for, we have 3 equations 21, 22 and 23 in 3 variables C12, C21 and eta naught, and we want to find a solution that is non-trivial where neither of these quantities goes to 0. So, there are 2 ways of doing this. I can look at these 3 equations, and any time I have 3 equations in 3 variables, the only time you have a non-trivial solution is when the determinant of the coefficients goes to 0. That is one way of solving it, and that is probably the most general way of solving it. I will restrict myself to a simpler case because I have essentially from 21 and 22 a closed form solution for C21 and C12 respectively. So, I will just substitute for C21 and C12 . So, essentially we are able to eliminate C1 and C2 by a substitution, and we find that we have an equation for eta naught, and the only time this equation in eta naught has a non-trivial solution for eta naught is when the rest of the coefficients are equated. Okay. So, that gives us this equation here, which we call our dispersion relation. This is important. Essentially what we have done is we found a condition that is written kind of nice and elegant here, that rho 1 omega plus I k u 1 squared plus rho 2 omega plus I k u 2 squared equals minus sigma k cubed. For a given k, we can use this equation to find omega. You notice that I have a quadratic equation in omega. So, for each k value, of course, given u1 and u2, rho 1 and rho 2, you have 2 roots in omega. Now, in general, if k is real, omega equals omega 1 2 are complex. So, in general I have 2 roots omega 1 and omega 2 which are in general complex. So, if I take, if the real part of omega 1 comma 2 is greater than 0, if the real part of either omega 1 or omega 2, it does not have to be both, if real part of either omega 1 or omega 2 is greater than 0, then the introduced in perturbation of wave number k will grow. Okay. So, if the converse being, if the real part of either omega 1 or omega 2 is less than 0, then the instability corresponding to that particular wave number k decays. For the decaying condition, the real part of both omega 1 and omega 2 must be negative. So, if either one of them is positive, then the instability is likely to grow. So, we will now use this our base dispersion relation simplified to see if we can understand this. As you see, rho 1, rho 2, u1, u2 given, we have a quadratic in omega. In general, I can write this equation down in a after expanding out the squares in this form. So, this is simply the dispersion relation written out as a quadratic of the form a omega squared plus b omega plus c equal to 0. Now, we are able to solve this equation closed form because we have a formula. And in here, I know a equals rho 1 plus rho 2. B equals I am going to not do the algebra here, we will just write down the solution. You can check this at your convenience. So, this is a closed form equation that would yield us two omegas, omega 1 comma 2, the one corresponding to the positive sign and 2 corresponding to the negative sign, and the term under the radical of course coming from our discriminant b square minus 4ac. Now, you notice that we remarked that if the real part of omega is positive, that is when you are likely to have an unstable perturbation. So, in this situation, if you notice, the first part here has an imaginary, is purely imaginary, which means this part can never be real. All the real part can only come from the discriminant under the radical. So, for omega to be greater than 0, or for real part of omega to be greater than 0, we know k squared times rho 1 rho 2 has to be greater than 0. So, leaving out the case where k is which is trivial, we are able to show that rho 1 rho 2 times u 1 minus u 2 the squared has to be greater than k times sigma times rho 1 plus rho 2. Okay. I want to draw your attention to two observations here. First thing is that if I interchange the subscripts 1 and 2 in this equation, the equation does not change. So, rho 1 becoming rho 2 and rho 2 becoming rho 1 with u 1 becoming u 2 and u 2 becoming u 1, equation is not changed. That basically means that the condition for instability is not governed by the absolute values of the densities or the velocities, and that we have no preferential direction whether 1 is superposed on 2 or 2 is superposed on 1, which should be obvious. The second point I want to draw your attention to is that it is also symmetric in the velocity. So, whether I simply replace u 1 with u 2 or u 2 with u 1, the only quantity that matters is u 1 minus u 2, the magnitude of the relative velocity u 1 minus u 2, not the absolute values u 1 or u 2. So, based on this we can set either u 1 or u 2 to 0 without loss of generality, essentially assuming that the frame of reference is moving with a velocity of with one of the fluids, either u 1 or u 2, and the condition still is remains unaltered. So, if I rewrite this, so this is the condition for instability, that all k for a given rho 1 rho 2 u 1 u 2 and sigma, all k less than this would have a positive value of the real part of omega. So, if this quantity is what we will call our k cutoff, it is always good to have some numbers. So, let us just pick some set of realistic numbers, all these are in SI units. For this case, I can quickly calculate k cutoff to be about 13.93, or if I want to convert back to lambda, so essentially if I have a breeze of 1 meter per second blowing on water, I have assumed rho 2 to be 1000 and rho 1 to be 1. So, if I have a breeze of 1 meter per second blowing on water at about water which is at rest, u 2 is 0, I am expecting waves whose wavelength is roughly about half a meter. And you will notice that as u 1 increases, k cutoff increases, which means lambda cutoff decreases. Now, remember this is the lambda cutoff, that is you will not see waves shorter than 0.45 meters. That is the meaning of lambda cutoff, k cutoff being 13.93. Now, so this is essentially information that we get from linear instability analysis, which was purely an analytical calculation, but leads us to draw some inferences in the physical space. of the kinds of waves that we would observe if we had a particular flow condition, velocities and densities. We will stop here and continue in the next lecture.